Today we're going to look at something called absolute dependent motion analysis of two particles, which is a lot of words, but has a pretty simple meaning. All it means is that we have two particles and their motion is dependent on one another. So the way that we commonly see a problem that looks like this is usually through pulleys. So if you can imagine, maybe I've got I'll use these square boxes to kind of represent particles, but we'll say that this particle here is attached to another one down here through a rope that goes over a pulley. Here's a pulley. Here's a pulley. It's attached to a corner of a table here. We have this pulley connecting these two blocks. I'll call this A and this guy B. Right, so maybe intuitively, maybe not, we can see that the motion of these two, the way that A moves, is dependent on the way that B moves. The way that B moves is dependent on A. They move each other. They're connected through this rope that goes over a pulley. So this is a common system that we see where the motion of something is related to something else. So this is the dependent motion analysis of these two particles. That's what we're going to be talking about. And so I'll kind of go through a procedure of how to approach these problems while looking at this kind of little example system. So what we want to do when we're trying to relate the movement of these two particles, A and B, what we want to do is establish a coordinate system. Right? Establish a coordinate system that has a fixed reference. I'll do it. This color's fine. So first step, establish a coordinate system. Right? Because as we've talked about with our curvilinear motion, rectilinear motion, these things, there may be different coordinate systems that are better to work in than others. Maybe rectangular, maybe polar, maybe the other one that I can't remember the name of right now. normal and tangential. Or other coordinate systems, right? These aren't finite. There are many different coordinate systems that you could use. So you want to establish what kind of coordinate system. Now in this one, it looks like an X and Y coordinate system is going to work pretty well for us. Since our direction, we're really only in those two directions, the X and Y. That's where our rope is. So establish a coordinate system and a fixed origin, or a fixed reference, or datum. So a fixed origin to work off of, or some kind of datum from a fixed point. So a point that's not moving relative to A and B, because A is moving, the rope is moving, some fixed reference. Right? And this is also what we're going to base our signs off of, whether we're in the positive or the negative. So what I mean by this is if we look over at this example over here on our side, I want to establish a fixed origin and kind of build off of that, build my references off of that. So I know the pulley itself does not move. I could use the center of my pulley, and this is commonly where we do it, is at the center of my pulley, nothing is moving. Right? The pulley itself isn't moving. This point is not moving. This is a fixed reference, where what I can do is I can draw my axes out from here. Right, so here's like an x-axis, or I'll just call it the datum for now, like my reference line. Datum. So these are the axes that are coming off of my reference point, like an origin. Right, I've selected that this is going to be my origin, and I'm going to measure my distance from there. So the location of B, I'm going to say this length from the datum to where B is SB, right? S being like the position. It's really representing, you can think of it also as like the length of the rope here. This distance from the datum to where particle B is SB. And the way that I've drawn this from the datum to B, this is also going to be my positive convention. So wherever my datum is, to wherever that particle is, this is going to be my positive convention. Right, so it could be any direction, but wherever I draw the direction of that position, because our position is a vector, wherever I draw that, that's going to be our positive convention. So we're going to assume if B is moving downwards, that's positive. And for A, if I draw from my datum to where A is located, I'm going to call this SA. This distance here, again, now we're going to assume that to the left is positive. If A is moving to the left, it's moving in a positive direction. A is moving to the right, then we're going to say it's moving in a negative direction. So all I've done is I've just kind of set up my datums and referenced A and B to those datums. I might be getting a little ahead of myself here, so let's check back in on our steps. So really, we established a datum. The next thing that we want to do is actually understand how everything relates together, which I skipped over a little bit because we can see kind of how these two things relate together, right? We can see that A and B are going to be dependent on each other. And if we can't see that, let me show you a short video of how this motion works in real life. So here we have our very basic pulley system where we've got a larger mass here on the left, and then we have a little mass here on the right. And these are just blocks that are kind of representing particles as we're talking about these pulley problems. So when we're describing this motion, when we're describing this total length, what we're going to have is the entire length of rope that goes up across and then down over the pulley, right? And we can see the motion that happens in real life if I'm trying to relate big block to little block, right? These motions are dependent on each other, because if I move big block, I can see that I start pulling this way, my little block down there moves upwards, right? And likewise, if I move little block down, then this big block moves closer in, right? Moves closer into that pulley system. And if I look at what's happening in the lengths, in those positions, if I define those positions, I can see that I have a changing length in this section of rope, right? Whether I'm moving the big block or whether I'm moving the little block, the length of this rope is changing, right? The position of this block really defines this length of rope if we use the fixed point here as a datum. Right, so the fixed point there as a datum for this pulley system, where I can see this length of rope is changing. And likewise, the length of rope that is down lower with our smaller mass is also changing. Longer or shorter, depending on which direction that position is being moved relative to the datum. But I notice that even when I move these blocks, right? These two blocks move in relation to one another. This length that goes across the pulley, this length never changes, right? It is constant from this datum point. If I draw like an axis, a y-axis up, down, or I draw an x-axis that is left, right, this quarter circle length of rope stays the same. When this moves, this stays the same. Where the other two lengths are changing, but this section of rope stays the same. This means that we can discard it in our calculations, because when we take a derivative of this position, of that length formula, so I have the length formula being the total length of this rope, so the length of the rope equals this length plus the length that goes over the arc plus the length that comes down. If I add those together, I get the total length. And if I take the derivative of that, then what I'm going to get is I have this position, this length is changing with respect to time when that block is undergoing movement. The lower length down here with the smaller block is changing too. But this length over the pulley is not, and the total length of the whole system remains unchanged, which means when we take that derivative, this length here drops out to 0, the total length drops out to 0, and all we're left with is the derivative of this rope with respect to time and the derivative of this rope length with respect to time. And those derivatives of those positions, right, defined as the relationship from a fixed point to our item of interest, this relationship is going to give us the velocity. And so we can relate that velocity and that position of our big block and our smaller block together. Right, so what we're doing here is we're relating the total length of what's going on over our pulley with the changing lengths from some relative fixed datum. Here it's the center of the pulley. We're relating those two lengths together, taking the derivative, and that's defining our relationship between velocity of one block to another block and acceleration of one block to another block. In that video, we could kind of see how the motion of A and B are dependent on each other, where if B moves down, then A moves to the right, and vice versa. Right, so these matter. It matters which direction these things are moving, because this is how we're going to set up those relationships, as we touched on in that video. So these relationships that I had brought up, where we're finding the total length, this is going to be our third step. Our third step in the process, after we kind of can mentally see how the system is moving, how things are interacting together, what we're going to do is find the total length of the cord. Find the total length of cord or rope or whatever is connecting those two particles A and B. So as we said in our video there, we have SB, which is changing, right? This section of rope, this length of rope from the datum to B is changing. That section we have is SB. Let me not put it over there, let me put it over here. SB, that's one length that we have. Another length that we have is that from the datum to A, that length of rope. Right, from the datum to A, that length of rope. Then we also have this little section, as we mentioned, going over the curve of this pulley. From datum to datum here, this curve, this length through here does not change. So plus that length, I'll call it length C for length of this curve over the pulley. That length does not change. And when we add all those together, we get the total length of the rope. So that's what we mean when we say find total length of cord. Find how long the cord is for each different section. Noting that we can actually ignore what the length is when lengths aren't changing. So like this LC, this length of the curve, we don't actually need it. Because when we're setting up these motions, these velocity and acceleration relationships, right, as we're doing with everything in this class, it's always relating position, velocity, acceleration. That's everything we've done so far, and we're still doing it. So the reason we wouldn't care about a constant length or a length that's not changing is because it's not going to give us a velocity. It's not going to give us an acceleration. When I take the derivative of a constant, I'm going to get 0. So if I look at this, my final step here when solving these dependent motion problems, this dependent motion analysis, is take the derivative. Take the derivative to find velocity, and again, repeat it, take the derivative again for acceleration. And then we can find and solve problems wanting to find distances or velocities or accelerations through these relationships, through this length of chord relationship, where if I want to now take the derivative of this guy, or look at how this is changing, right? So my SB, change in SB over time, plus my change, I don't know why I wrote an uppercase delta over there, but that's neither here nor there, plus my length over the pulley is constant, that's 0. My length total is constant, that's 0. So it gives me this relationship between the changing position of A and B as they're related to each other. And if I go through and solve this, if I'm finding, like, say, their velocity relationship between A and B, then what I'm going to get is I have delta SB over dt, delta SA over dt. Again, those are just velocities. Those derivatives of position is velocity. I'm going to get VB equals negative VA. Right? And we can see this. This makes sense for this system. Because I can see if B is moving downwards, which again we said that's our positive direction, right? Our SB is positive in the negative coming down from the datum to B. Our SA positive is to the left. We can see that SA is moving to the right if B is moving down, right? So it's going back towards the datum. It's going in the opposite direction of SA, making it negative. And it makes sense that they would be going at the same velocity. There's nowhere else for that velocity to go. There's nothing else in the system taking on velocity from it. So it makes sense that A and B are going at the same speed, just in the opposite direction of each other from this datum that we've set up. And this holds true with the acceleration as well. If you wanted to take another derivative, we'd get the acceleration of B is negative the acceleration of particle A. So the whole goal here with our absolute dependent motion analysis of two particles is that we have two particles. They are dependent on the motion of the other, right? They are usually connected together in some way, usually through a rope in a pulley system. And what we have to do is associate those lengths of rope that are changing in order to find and understand how the velocities of the particles of the system relate to each other. So this was a fairly straightforward, simple example, but let's take a look at something a little bit more complex. So in this example, we have this cable pulley system on the left, and it says if the end cable at A is pulled down with a speed of 2 meters per second, determine the speed at which block B rises. So if we take a look at the system over here, we can notice a few things, right? So we do see this hand at A pulling A down by 2 meters per second. That's our velocity at A there. But we also notice that there are really 2 ropes here. So unlike the last example where we had 1 rope connecting things, there are 2 ropes involved, where we have a rope from A, goes over pulley D, goes through pulley C, up to the ceiling. Then there's a second, not connected, but also connected to the same system, but a different rope. Down from C through this pulley that's holding the weight B. We have 2 cables. 2 cables here that we're looking at. And so our first thing to do is establish a coordinate system and figure out what datum we want to use for these 2 pulley system to relate A and B together, right? Relating those velocities together so we can find that speed at B. So to set that datum, I want to pick a fixed point that's not moving. Fixed point that's not moving. Again, those are usually on the pulleys themselves, usually that's a good place to put them, a pulley that is not moving. So if we think about how this system is moving, when I'm pulling down at A, what it's gonna do is it goes over D, and then that rope there that's cradling pulley C is getting moved upwards. Right, so pulley C is not stationary, it's moving. But pulley D is attached to the ceiling. Pulley D does not move. Right, it stays there. Unlike our other pulley down at the bottom, the pulley supporting B, if C is moving up, then that pulley down there holding B is also moving up. So D is our pulley that is not moving. And so if I go ahead and put a datum at the center of D, and I say, okay, this point is not moving. This is going to be my reference point. Let's make an axis. Let's make a datum. Notice that everything I have above this datum is not moving. It's not moving. Sorry, I was going to see if I could maybe have a highlighter to show. Right, so this portion, yeah, there we go. This portion that arcs over CD, that length is not changing. This length and this length of those blue and orange pulleys, they aren't changing. Really, it's all of those lengths below it that are going to be changing. So if I have on here my distance from the datum to A, right? This is SA. That's my position from the datum at D to A. I can also find my position, my distance from the datum at D to C. Right? This is my position from datum downwards. SA is changing, right? That hand is pulling down at A. A is moving downwards. That position is changing. C is changing, right? Because A is moving down, the way the motion is having it is that pulley at C is moving up. And so each of these lengths of rope, let me get my highlighter back out. Each of these lengths of rope from the datum down to the center of C, ones that I've kind of highlighted in red here, these are changing. This SC is changing. Both of them have the length of SC, but it's changing because pulley C is moving up. But notice this portion down here, right, this cradle that it's sitting in, we're not actually going to have to account for this length because the length here is not changing. Right, this length of rope that is sitting up in the cradle at C, that length is not changing. But those side lengths SC are. And so where it sits, the cradle does not change. That semicircle where the length is constant, we can write it in, but we don't have to account for it in our calculations. And I'll show you that when we write these down. Actually, let's do that now. Let's write it down. Let's write it down for our orange pulley system there. Right, so if I want to write out this length of rope, total length of rope for this ACD pulley system, I'm going to have the length SA. Okay, that starts at A, goes up to D. Then at D, we enter that arc. Right, this is a constant length over the top of D, this semicircle. I call it the length of the string of the pulley over D. Then I have SC. Right, this length from the datum to the center of C. I'm going to call that the position of SC. Then we're going to come around the bottom of C. Again, this semicircle of length is a constant length. It's not changing. There's always going to be some length of rope underneath that pulley at C. Then we're going to come back up. Oops. back up. This is from C to the datum. That is, again, SC, same length as the other side. And then finally, we have some length that is from the datum to the ceiling. It's a not changing length. It's a constant length. It's not going to be changing at all. I'm going to call it L to ceiling, LTC, length to ceiling. So now, when I take the derivative of this to relate the speed, right, take the derivative of everything, all of those constant lengths do not get a speed. They do not have velocity. They do not get a speed. They get 0 is VA plus VC. Other L, this L goes, this L goes. This SC is gonna be the derivative, becomes VC. And that's a constant length, so it goes to 0. So what we end up with is this relationship VA equals -2 C. Right, so we can find what the speed that pulley at C is rising at. Right, VA we said is 2 meters per second, and it's going down, which is the direction of SA, so that's the positive convention. So VC is -1/2 VA, which is 1/2 of 2. So VC is -1 meter per second squared. So -1 means it's moving up. Again, we said if you're going down from the datum is positive. So since C is moving up towards the datum, this means that it's negative. It's in the opposite direction. -1 meter per second. And so that was just the relationship of that orange pulley of A to D to C. But we didn't need to find, like, we weren't asked explicitly to find that velocity of C. What we really wanted to find was the speed at B, right? But we needed that relationship for this other pulley. Go ahead and take a look at this other pulley here that is part of this system. From my datum, if I go down to the pulley B, this is going to be our position of B. So getting my lengths, this is a totally separate length equation. Because it is a separate rope, a separate pulley, separate cord, it gets its own length system, where its total length is going to be, we have this upper top part. I'm going to go top down, basically, like kind of swing around the J shape. So top down, I'm going to come down from the ceiling, so length to the ceiling. That's a constant, it's not changing. Then I have this whole length from the datum down to the pulley B. Here's pulley B, down to pulley B. That's going to be SB, right? That's where B is located. Plus this length around the bottom of the pulley. Again, this length is not changing. That semicircle underneath the pulley, not changing. I call that the length of B. And then I have this one last little length, right, where I'm connecting into pulley C. And so this distance here, I can actually represent by using SB and SC, right? Because if I want to find this distance is just SB minus SC. Right, this right here is SB minus SC, and that's how I'm going to put it into this relationship. Plus SB minus SC. And that's it. That's all of the parts of the rope. That's the total length. So we're going to go ahead and get a velocity relationship now. I take the derivatives. These unchanging lengths go to 0. I get 0 is SB plus SB, that's 2SB, minus SC. which is going to give me that SB equals 1/2 SC. Or sorry, these are velocities because I'm taking that derivative. Sorry, this is 0 is 2 VB. Again, because we took that derivative there. Means VB is 1/2. Oh my gosh, VC? Too sleepy. Making mistakes here, goodness. Alright, so since we have VC, we can plug it into this guy and find what that speed at B is. So 1/2 of VC is going to be negative 1/2 meters per second, or negative 0.5 meters per second. That's our velocity at B. You see, we're going 1/4 the speed that A is pulling with, right? A is being pulled down at 2 meters per second, whereas B is being pulled up. Again, that's our negative direction is up. I know it feels counterintuitive, but that's the way our datum is set up. Is negative 0.5 meters per second. Negative means it's rising. Let's go ahead and take a look at another example. In this example, we have a pulley system now that is interacting with a motor. So it says, starting from rest, the cable can be wound into the drum of the motor at a rate of VA equals 3t squared, where t's in seconds. Determine the time needed to lift the load 7 feet. All right, so we want to find out how long does it take for this crate to move upwards by 7 feet. So we've got a distance. We're looking for a time. Right? Time is question mark. We don't know what time is. We can relate time and distance through a velocity. So if we find the velocity of this crate B here, we'll call it crate B because it's attached to pulley B, so I'm going to call it B. Just this general, this whole thing. This is connected. This is the easiest connection. It's one single rope. So this velocity of B, whatever this is, whatever's happening here, we can relate that with position and time to find that time. Given that we know velocity of A is being wound into the drum, so at A here, VA is going to be 3t squared. Right, a rate of 3t squared. So again, when you're approaching these pulley problems, what we're going to do first is we're going to establish our coordinate system, establish that datum, understand how this thing is moving, and then we're going to start setting up those length relationships so that we can find the velocity relationship. So looking at this system, I've got 3 different ropes this time. Right, so if we look at this, my bold guy out again, I've got not only this I'll start right to left, this cable around B that connects into C, but then I also have this cable from the ceiling around C that connects to D, and then I have this cable from A around D up to the ceiling. So 3 different cables at work here, meaning that we're going to have 3 different length equations to work with in order to get that A to relate all the way through all of these pulleys to B. So let's look at what's not moving. How am I going to set this reference? Where would be a good datum, preferably a pulley center, that is not moving? And in this system, I only have 1 pulley, again, that is not moving. Pulley doesn't even get a name, that's how unimportant it is. because it's our datum. It's our datum line. Everything above that datum, we don't need to account for. None of those lengths are changing. Only going to be accounting for those changing lengths. Right, so I'm going to have the distance from the datum to A, going to be our SA. Again, now positive is down once again. And downwards is positive. The distance from the datum to pulley D, call that SD. I'm really going to run out of room for these. Everything's too close together. SD. My distance from the datum down to C, position C. From the datum down to B, that's our position B. So let's go ahead and, I'm going to do these right to left actually. I'm going to start with what looks like the simplest pulley, which is this pulley around B. Pulley around B. And again, I only need those lengths of things that are changing so that I get the length is going to be SB. So again, that SB is the distance from the datum down to B. I can ignore this curve here, right? That length is constant. I mean, include it if you want to, more power to you, but you really don't need to. So we have that SB, then we come around the curve, and then we come up by this little distance. Little distance here, much like in the last one. That little distance there is SB minus SC. We said we have SB plus the little distance over the pulley of B. That length is not changing. Plus SB minus SC. This distance here. SB minus SC. I can take the derivative of that. 0 is VB plus VB minus VC. So I get VC is 2 VB. Let's keep on moving it. If I look at my next pulley, that pulley around C, I'm going to have from the datum down to the pulley at C, that length, that position is SC. Then I come around the curve of the bottom of C. That's a constant. That's just the length around the bottom of C. Then I have this little one up to E. That little length up to D. So now, I write this out. For that next pulley, the total length is going to be SC plus that length over the curve plus this distance here is going to be SC minus SD. Right? The difference in those gives us that little length. SC minus SD. Take my derivatives, my lengths disappear. 0 is VC plus VC minus VD. VD is 2VC. And then finally the big guns. Right? Big, long pulley to my left. We start at the datum, come down to D. That distance is SD. The curve around the bottom here, that's a constant length. Then I have SD again. Right, so there's 2 SDs there. I don't need to account for this length over the top here. It's a constant. And then I have my distance to SA. So if I write down this length, I'm going to get my total length is SD plus SD plus SA. Right? I don't need those lengths over the curves. They're not important to me. When I take a derivative, I'm going to get 0 equals 2 VD plus VA, or that VA equals -2 VD. So now I have all of these relationships to each other. I can start relating stuff. I can start plugging stuff in. Right? So I'm trying to relate A and B together because I want to know what that velocity at B is. That's what I'm looking for. So I can plug in my VA equals -2 VD and plug this guy in. So that gives me VA equals -2 times 2VC. Then for VC, I can plug in my B relationship. So I get VA equals -4, and then VC we said is 2 VB. So VA is -8 VB. And it makes sense. We would expect them to be opposites of each other, right? A is moving in the positive direction. B is moving in the opposite direction. Okay, so we said down is positive. Means that our velocity for B should be negative. And our VA, we were given something for that, right? Our VA is 3t squared. So 3t squared equals -8 VB. This means that our VB is -3/8 t squared. Which is all great and all. But what we wanted was the time. Time to lift the load 7 feet. Thankfully, we have a relationship between position, velocity, and time. Right? Our position, or if we take the derivative of position, we get velocity. So if we integrate velocity, we can get our position. We know how far B is being lifted, so we can find that relationship. We can find that time. So we have VB is ESB dt. So I plug in VB over here, that's -3/8 t squared dt equals how that position of B is changing. And then I can integrate either side. And by either side, I really mean both sides. With our time side being from 0 to t, because we're looking for the time, we don't know what that is. And then for our SB, we can either go ahead and plug in that 7 now, but I think I'm going to wait. I think I'm going to wait and we'll plug it in at the end. I'm just going to go 0 to SB for like a general equation. So that way I can get the general relationship between position and time. So here I'm going to get SB is -1/8 t cubed. -1/8 t cubed. Now remember, I'm lifting this box by 7 feet. The box is going up 7 feet. It's going against the datum direction. Datum direction is down positive. We are lifting by 7 feet, which means that SB, that change in position from where we were lifting up, we are lifting a -7 feet. Right? It started at a position of 0, you could say, and then as it's getting closer to the datum, it's going negative in our negative direction. Opposite of the position we expected, the way that we drew our datum. So once we know that, once we recognize that our lift is going to be a -7 feet, we can plug that in, and then we can solve for t. So this is just a matter of plugging this into your calculator, and we get that it takes 3.0 0.83 seconds. The lift at 7 feet. That's pretty quick. I mean, 7 feet, that's taller than most people. To do that in 4 seconds, pretty quick. But this is how we approach these problems where we have two particles, their motion depends on each other. It's usually pulley problems. We establish that datum, we understand the relationship of how things are moving with respect to each other, and we do that through setting up these relationship equations of the lengths, taking derivatives to find velocities or accelerations, whatever the question's asking of us, using those velocity, position, acceleration relationships that we've been working with all throughout the class so far to find whatever it is that we're looking for.